Alright, so in this video we're going to compare polar graphs with rectangular graphs and convert from polar to rectangular. We're going to start with this idea that any one point in a plane can be labeled with an x and a y coordinate, but it can also be thought of as being a distance from the origin and an angle. And so we have that same point right here has two different names. It could be xy or it could be r theta. And given that relationship in the right triangle that the x and y make, you can come up with all of these relationships. You should pause the video right now and see what you can fill in on your own. So welcome back. Hopefully you could see from your picture, since cosine of theta is adjacent over hypotenuse, you get x over r. And sine of theta is opposite over hypotenuse, which is y over r. Tangent of theta is opposite over adjacent, y over x. Secant of theta is the reciprocal of cosine, so it's going to be r over x. Cosecant of theta is the reciprocal of sine. Remember, every pair needs a co. Sine does not have a co, cosecant does. It's going to be r over y. Cotangent is the reciprocal of tangent, and we get x over y. So the triangle itself gives us those 6 trig ratios. Now, when we are trying to convert between r and theta to x and y, Pythagorean theorem tells us that r is the square root of x squared plus y squared. And theta is going to be tangent inverse of y over x. And the one caveat I will make is that you always need to check your quadrant, because if you use your calculator in particular to do tan inverse, it is going to give you an answer between negative 90 and 90 or negative pi over 2 and pi over 2. If you are in quadrant 2 or 3, you are never going to get the correct answer out of inverse tangent. You need to take your inverse tangent answer and add 180 degrees or pi radians, depending. X coordinate from this cosine of theta is x over r. We can see that x is equal to r cosine theta. And y, similarly, is going to equal r sine of theta. Now we're going to use these relationships to look at different graphs. So right now we're going to start with our calculator. We're going to plot the graph of r equals 3 cosecant theta. And so we want to be, here's my window. I'm working in degrees for now. 0 to 360 in steps of 5. X is negative 7 to 7. Y is negative 6 to 6. And I'm going to put my y equals 3 cosecant. And remember, cosecant is 1 over sine. So I could do 3 divided by sine of theta. And let's take a look and see what that looks like. Whoa. So there it is. And this looks like the equation y equals 3. So why would that be? Well, we're going to do some converting. So we're going to start with our r equals 3 cosecant of theta. And I saw from my slide before that I can replace cosecant of theta with r over y. So I'm going to do that. R equals 3 r over y. I want to end up with a y equals, so I want to get this r out of the bottom. So I'm going to multiply both sides by y. I want to get the y out of the bottom. So I have y times r is 3r. And to get y alone, I'm going to divide my r. And voila, we end up with the equation y equals 3. So simple substitution and then some algebraic manipulation. And you can see that r cosecant of theta is y equals 3. In a similar manner, why don't you stop the video and see if you can do r is 5 secant theta. And let's see then what we would get if it matches our graph. So hopefully you got the equation. In this case, we're not going to get a y equals equation. We are going to get x equal to 5. If I look in here and I plot it, when I do 5, and secant is 1 over cosine of theta, and I look at my graph, there's my x equals 5, right? And where does that come from? Very similarly, r is 5. Secant theta we're going to replace with r over x. I multiply my x up, divide my r, and there we have it. So those are fairly simple. So to get a vertical or horizontal line, in rectangular, it's a fairly simple equation. In polar, it's a little bit more complicated. R equals 6 cosine theta. So let's take a look at what that looks like. Now we did this investigation yesterday. You should be able to tell me already what it looks like without using your calculator, because we should know that is going to be a circle with a diameter of 6 and centered along the x-axis. Let's check it out and make sure that that is true. So I'm going to have 6, let's get rid of that divide, and there's my graph. It doesn't look particularly circular, but it is. That has more to do with my window than anything else. So I said yesterday we were going to look at why this happens, and so we are. In this case, I am going to replace both r and cosine theta with what they are equal to using x and y, but I'm going to hold off on the r first, actually, because it's going to make it a little bit easier. So I'm going to start with cosine theta is the same as x over r. And there's more than one way you can solve this, but I'm going to use this x over r first. And I'm going to keep my r for a little bit, because what's going to happen here, I want to end up with no r's with only x's and y's. I am going to multiply by r on both sides and get r squared is 6x. And I did that because now I know that r squared is x squared plus y squared. And I know that because r is the square root of x squared plus y squared. And so squaring the square root undoes the square root. Right, so now hopefully you can see that this is going to be a circle, right? If I subtract over x squared minus 6x plus y squared equals 0, you should recognize from our conic sections unit that x and y have the same coefficient of 1 and they are both positive. That's going to make a circle. We're going to take this one step farther and we're going to complete the square to show that this is a circle centered at 3, 0 with a radius of 3. And so this little completing the square is good review for the final. So if you wanted to pause the video and try to complete the square on your own, it would be good practice. But here we go. So I'm going to say x squared minus 6x plus some number, and then I'm going to subtract that number, plus y squared is 0. Because what I want is a perfect square out of this. And what we do is we take our negative 6 and we cut that in half. So x squared minus 6x is the beginning of the perfect square x minus 3 squared. And if I do this out, this thing right here, I will get x squared minus 6x. I will also get plus 9. So to replace something and end up with x minus 3 squared, I needed a plus 9 there. Well, I can't just add without also subtracting. And now my next step is I'm going to actually keep my y squared, but I'm going to move that 9 over by adding 9 to that side. Or in this step, when I added the 9 here, I could have added 9 to the other side. That's another way to balance. But here I have my circle with center of 3, 0, and radius is square root of 9, which is 3. All right, I think we're going to make our polar window just a little bit smaller. We're going to work with some graphs that are a little bit smaller. So I'm going to go now from -2 to 2, and again -2 to 2. All right, and what's next? Okay, so we're going to try and plot this graph first and see what we get. So I'm going to clear that and do 1 divided by, I need parentheses so that I divide by the whole bottom. And when we look at this picture, whoa, what do we get? What kind of shape is this? If you notice, today we're doing a little foray back into our conic section unit, and this is a hyperbola. Where does this hyperbola come from? Right, we're going to turn it into a y equals. So I'm going to start here again. I'm going to leave r for now until I get rid of some stuff. 2 cosine of theta is r, or is x over r. Oops. Okay. Now, I don't like x in the bottom. I'm going to get rid of this by multiplying both sides by 1 plus 2x over r. I don't really have a lot of space. And I'm going to distribute my r in here, and I get r plus 2x equals 1, which is quite a bit simpler because the other side will cancel. Now I'm going to turn my r into root x squared plus y squared. So now I've gotten rid of all r's. See that r right there? R is the square root of x squared plus y squared. I want to see how do I get a hyperbola? I don't have any square roots, so I want to get rid of the square roots. But first, to make it simpler, I'm going to subtract my 2x over. And now when I square, because that's my next step, I want to get rid of this square root. Squaring undoes the square root. And over here, I get 1 minus 4x plus 4x squared. And now I have x squareds on both sides. To figure out that this is a hyperbola, I need to collect all my x squareds and y squareds on the same side. And if x squared and y squared have the same coefficient, that's a circle. X squared and y squared are different coefficients, but both positive, that's my ellipse. And if one is positive and one is negative, that's going to be my hyperbola. And indeed, I'm going to subtract my 4x squared, and I can again add my 4x. And this side becomes negative 3x squared plus 4x plus y squared equals 1, which is indeed a hyperbola. I have a negative coefficient on my x squared, and I have a positive coefficient on my y squared. And I'm not going to complete the square to figure out more about that hyperbola, although we could. But it is definitely a hyperbola. All right, so now I have another one. I have 2 minus 1. What kind of shape is this? So we have a similar kind of graph. 1 over parentheses 2 minus 1 cosine theta. And this gets us our ellipse. All right. Similar method here. R equals 1 over 2 minus cosine theta is x over r. I'm going to multiply that up on both sides, right? 2 minus x over r here, 2 minus x over r there. This is going to cancel. And I get 2r minus x is 1. I'm going to add my x over. I'm going to replace my r with square root of x squared plus y squared. And I'm going to square both sides right here. When I square the 2, I get 4. And when I square the square root, I get x squared plus y squared. And when I square my other side, I get x squared plus 2x plus 1. Distributing here gives me 4x squared plus 4y squared. And again, to see what kind of conic section we have, I need to collect my x squareds on the same side. So I'm going to subtract that over. I can subtract the 2x. What's left over there is the 1. And this is an ellipse. My x squared term and my y squared term, when they're on the same side, both have the same coefficient, or different coefficients, but they are both positive. So there's my ellipse. Okay, so we have one more here. What kind of shape is this? So I'm going to make a little bigger a, or a little bigger number on top, and I'm going to oops, where am I? There we go. 4 minus 4. In this case, I'm switching to sine as well, which it's not about the sine and cosine that makes these graphs what they are, but here's my last picture. Ooh. This one, it's kind of hard to see. Looks like maybe it could be part of an ellipse, but it is actually a parabola. And so how do we get a parabola out of this? Similarly, 9 over 4 minus 4. In this case, sine of theta is y over r. I will multiply the bottom up, right? So I get 4r minus 4y equals 9. I multiplied and distributed all at once. Hopefully you're on board. And this 4, r becomes x squared plus y squared. I'm going to add the 4y over. And now I'm going to square both sides. 4 squared is 16. The root squared gets rid of the root. And when I square this, here, we'll do that. I get 16y squared plus I'll have a 36 and another 36. And I will have an 81. This side becomes 16x squared plus 16y squared. And when I collect x squareds and y squareds on the same side, or attempt to, when I subtract 16y squared, I end up with 16x squared and no y squareds. And this is a parabola, because only one of my terms is squared. And it should sort of make sense that when these two numbers are the same, I end up with this 4 in front of my root, and I have the same 4 here, and I end up squaring both of those 4's, and I get the same coefficient on my y's. And then when I subtract, they disappear. So really quickly, what do A and B tell us about the graph? If we have this general form, they tell us what conic section we have. And if, let's see, which one is it? So if A is less than B, we have our hyperbola. That was the first case. We had 1 plus 2 cosine theta. If A is greater than B, then we got the ellipse. And I think if A equals B, we get the parabola. And then what difference does using sine or cosine make? That's going to change sort of which way we open. If you think of the parabola or the hyperbola, or it's going to change our stretches. So it changes the ways we open or the which way we stretch. Yeah. So hopefully you have a little better understanding of what the how the conic sections come out of polar graphs and how to convert some polar graphs.